In this video, I will talk about regression with indicator variables in R. Before you watch this video, please make sure that you have watched my other video called Regression with Indicator Variables. I have opened up this R script here. I have downloaded the data and that is wage1.csv, and I have put it into this directory here. And I highlighted the script, I run it, and these are the results shown in the console window, which for you typically would be at the bottom here. So what we are going to talk today about is regression with indicator variables. This is when we have a 0, 1 dummy variable. So first we would talk about single indicator variable, then we would talk about interaction terms with another indicator variable, several related indicator variables, interaction terms with a non-indicator variable, and then we will talk about the F-test and the Chow test for differences across groups. As I said, for today's exercise, we will be using the data wage 1. So we would be reading in this file into our data frame, and then we would be seeing the first 10 observations. We would see the structure of the data, and using Stargazer, we would summarize the data for these selected variables from the data set. So let's see what we can see in the data. Here's how the data looks like. Here we have wage. This is measured in dollars. These are the first 10 observations in the data. We have education in terms of number of years, experience in number of years, tenure with the company, how many years a person has been with the company in number of years. And then we have two indicator variables, one for female and one for married. So here, if the person is a female, it gets a 1. If the person is male, it gets a 0. And if the person is married, it gets a 1. If the person is not married, it gets a 0. So these two are indicator or dummy variables. We have 526 observations, and the 6 variables that we selected here, these are again the first few observations. And using Stargazer, summarizing the data, this is the average of the wage. So here for this data set, which is older, we have $5.89 as the average wage across all people in the sample, and these are the other summary statistics. So notice that here the summary statistics shows that about 47% of the people in the sample are female, the rest are male, and about 60% in the sample are married and the rest are not married. Okay, so if we would like to calculate the average wage, we can do it in two different ways. So the first way is to actually use a linear model, and then wage would be the dependent variable. And here, this one means that we're regressing it only on a constant using the wage 1 data set, and we're going to summarize it. And this is the only coefficient that we have. Basically, this is only the intercept because we do not have any other independent variables here. And so here, this 5.89 is exactly the same as if we use Stargazer and we select the variable wage from the data frame wage 1, and we basically summarize it with Stargazer. So this 5.89 is exactly the same as this 5.89, which is the intercept of the regression of wage here regressed on a constant. Now, things would get a little bit more complicated if we want to have a regression of wage on female. So the way to do this, we would use linear model, wage dependent variable, and female would be our independent variable. Now notice this female is an indicator 0, 1 variable. So using this data set and then summarizing the results, here now we have an intercept, and here we have a coefficient on female. So the way to interpret this is that females here are getting $2.51 lower wages than males. Now, That's how to interpret this coefficient here. And here we could actually see what the average salaries for male and female are from intercept. So if the person is male, for them female would be equal to 0. Therefore, this one would be the average salary for males. Uh, and then for females, the average salary would be this number plus, because this female would be equal to 1 plus this coefficient, but it's with a minus. So this number 5.09 plus of the minus 2.51 would actually be the average salary for females. Okay, so now let's go ahead and actually plot these this linear model on a graph. And the way to do it here would be to use ggplot. We would be using this data set. And here on the X, on the horizontal line, we would have female. On the vertical line, we would have wage. We would be using points, and geom smooth, we would be using um, a fitted line, and the method would be linear model. And here for standard errors, false, because we're not going to be plotting any standard errors. So here's, if we execute this line, this is basically what we're going to see here as a graph. So what we are seeing here is basically this was the regression line that we saw here. The intercept was 7 point something, and then the slope here was the negative 2.51. Notice that the data is basically clustered at 0 and at 1 because on the horizontal line we have female. That female has only two values, 0 and 1. So effectively, these data points here are all for males, and these data points here are all for female. And that's how a regression line looks like. So it looks a little bit strange if we just have one independent variable that is an indicator variable. But this is how a regression like would look like. So now next, let's go ahead and summarize the data for males and females. And the way we would be using the data frame wage 1, select the variable wage, and then we would be splitting from the data frame wage 1, the variable female. So we would be splitting it into two groups, and then walk stargazer would basically give us the summary statistics for each group. So what this final line here gives you basically the average for wage for males and the wage for females. So notice how the average wage for male is 7.099. This is exactly this coefficient here. Why? Because for males, that female would be equal to 0. So basically, that's all we have in the regression. So that's why that's the average wage. And for female, this average wage would be, because female is equal to 1, we would be summing up this coefficient and this coefficient. And because this is a negative coefficient, when we sum up these two coefficients, that would be the number that we get, 4.58. So again, this is the average salary for male, average salary for female. Notice that the average salary for female is exactly this $2.51 dollars that is lower than the one for males. So everything kind of checks and balances no matter what method we use. The next thing that we can do here is a t-test for average wage for females and males, because we just are basically comparing the wage for males and females. We don't need a whole regression. We could just use the t-test. So the way to do this is t.test formula. We have wage on female. And here we would be getting the mean, the test statistic, and p-value. And so here we have this uh, the test statistic and the p-value here. And we have the means for two groups. And basically, whether or not we use a t-test or a regression as we had here above, we would be actually reaching the same conclusion as before. Okay, so the next thing we can do is let's generate an indicator variable for male, and we would be using male equals 1 minus female, and using the mutate function, we would be uh, ascribing this male variable back into the data frame. And now let's run the regression as we had before of wage on female. And then let's run another one of wage on male and see what we get here. Okay, so this is the regression here that we have of um, wage regressed on male. And this is repeating from what we had above. But if we regress wage on female, these are going to be the regression results here. So notice two things. The first one is that the coefficient on female is exactly of the same size, the same magnitude, and also exactly the same significance. The only thing that's different from this coefficient to this coefficient is the sign. So here it's a negative, here's a positive. And the reason for that is if we say in this regression that females are getting $2.51 lower wages than males, here we would be saying that males are getting $2.51 higher wages than females. Remember, because the reference category here for males is females, and the reference category for females is males. So that's why these have to be opposite results. Now, this coefficient here is also the average wages for females. Why? Because for females, that male dummy variable would be equal to 0. And therefore, we have this is the average wage for females. Now, if we want to calculate the average wage for males, males would be equal to 1, so we need to do this number plus this number, which would be exactly the 7.09 that we have here for average salary of males. So again, checks and balances, we get everything uh, you can derive one from the other. Okay, so the next thing is let's try to estimate a regression that both male and female are included together in the regression. So if we attempt to do that, so we attempt to run a regression of wage on female and male, we cannot do this because of perfect linearity. And so you see how that variable male is being dropped from the model. So alternatively, you can actually estimate a regression model with both of them, male and female, but that has no constant. The way to do that is you include here 0 plus, which means no constant, because otherwise the constant would be a 1 here if we have a constant in the regression. So these are the results that we get here. Notice that this is exactly the average salary for male. This is exactly the average salary for female. But again, most people would not use this approach of not having an intercept in the regression. Okay, so moving on, let's talk about interaction terms with another indicator variable. So here we would talk not only about female, but as a indicator variable, but let's talk about also married as an indicator variable. So we would be generating some indicator variable here. So we have married in the data set, but let's generate a variable called single, which would be 1 minus married. So basically the opposite of married. And let's include this in the data frame. So we also should calculate a few categories. And basically, I will be multiplying female times single, male times single, female times married, and male times married. So basically, I have all the 4 combinations of whether the person is male or female and whether the person is single or married. And so here is how I'm going to, here's how I am calculating these interaction terms. And these are the variable names that I'm calling of, that I'm giving of these interaction terms. So here, let's go ahead and list these interaction variables, indicator variables and their interaction terms. And so from the data set, I will select the original variables that I have, the 4 variables and the 4 interaction terms. And let's see the first 10 observations. So here they are. And the way to form these is, so I'm noticing here for the first observation, that's a female. And this first observation is a single person. You see it here? And so female times single is basically multiplying female times single, and that's why it's a 1. And everything else is a 0 as we multiply male times single, female times married, and so forth. For the second person, we actually have another female who happens to be married. So here, the only interaction term that we're going to have here is female times married would be equal to 1. Everything else would be equal to 0 and so forth. So this is how this data would now look like with the interaction terms. And if we estimate a regression with all four categories, R will drop 1. So if we attempt to put all four of these categorical variables, R would drop 1 because if you actually sum up this one plus this one plus this one plus this one, you're actually going to get a 1 for all of them. So these, if we attempt to include all four categories, that's going to be perfectly collinear with the constant in the model, so you cannot do this. So here's this model that we can attempt to estimate. Here we have wage regressed on all of the four interaction terms. And R is basically telling you that one of them needs to be dropped, and so the other ones are left. So again, if you forget that they are related to each other and you need to drop one that would serve as the reference category, the software would help you do that. But if you remember, which is the correct approach, let's do a regression with male times single as the reference category. So what that means is that we're going to be not including this interaction term in the model. So everything else will be interpreted with respect to this reference category that is not in the model. So to do that, we are going to be running a linear model of wage, and you see how we have the three interaction terms, but not the male single included in this model. Okay, so now when we estimate this model, these are the results that we are going to be getting. So these are different coefficients that we have here on the interaction terms. So now, if we want to know what is the marginal effect for being female and single on wage, so basically that would be the coefficient that we see here. And the marginal effects for being female and married on wage, that would be the coefficient that we see here on married. So basically, if the person is female and single, they would be getting basically 55 cents less in salary compared to the reference category, which is male and single. And if we have uh, a person who is female and married, they will be getting 60 cents less compared to the being male and single, compared to being male and single. So that's one way in which we can do interaction terms. Another way in which we can do interaction terms are to have categories of male, married, and then the interaction of just female and married, but to include the original terms here for female and married. So in order to do that, let's first calculate the interaction term of female and married. We would be calling it like that, female times married as the name of the new variable. And now let's run a regression that has the female, the married, and then the interaction term of the two. So a lot of studies would actually have interaction terms more often done like this than like this, but you know, some studies have it done like that as well. So these are the results that we see here. So here we have a coefficient on female, on married, and the interaction term for them. So now, if we want to calculate the marginal effect for being female and single on wage, that would be basically the coefficient on female right here, because for a single person, this married would be equal to 0, therefore this interaction term would be equal to 0, so we only have this coefficient. Now, the marginal effect for female and married on wage would be basically we would need to sum up these three coefficients here, and because if a person is single and married, these all of these interaction terms would be equal to 1. So if we sum all of that up, we would get the minus 0.60. So if you notice, these two numbers, these two marginal effects are exactly the same as we had before in the other way we did the interaction terms. So again, we are now comparing being female and single or being female and married to the reference category, which is being single male. And that's our reference category. Okay, moving on, let's talk about several related indicator variables and how we can possibly use them in a regression model. So here, if we have several related indicator variables, we also need to drop one as the reference category. So here, let's have variables for regions. So here we have the North, Central, South, and West region. And so from these variables, we can actually calculate another indicator variable, which is East, which is equal to 1 minus these. So basically now all of these regional variables would sum up to 1. So let's go ahead, select all of these regional variables, and then summarize them with Stargazer. And this is what we're going to see here. So the way to interpret this is that if we have people living in the North Central region, their average wage is $5.71. If they live in the South, their average wage is $5.38. If they live in the West, this is their average wage. And if they live in the East, this is their average wage. So now notice how each of the average wages from one region to the next compares to each other, because when we run regression, we would basically be comparing these. So if you're noticing here, how does the average wage in the West compare to the East? Well, it is basically 24 cents higher than this one. How does the average wage in the South compare to the average wage in the East? Well, if you look at this, it's basically almost a dollar, not quite, but almost a dollar less than the East, and so forth. So now let's see exactly the same differences here using a regression model. So how we're going to do this is let's run a regression. So here we would have a linear model, wage dependent variable, and we would be including all of these regions as independent variables, but notice that we're going to skip one of them, East, which would not be included here, which would serve as the reference category. So when we interpret the results, we need to interpret them in comparison to the missing category that serves as a reference category. So these are the regression results. That's how it looks like. So here, if we want to interpret what are the wages, average wages in the West, we would say that the average wages in the West are 24 cents higher than the average wages in the East, because East was our reference category. That's not included in the model. You see, it's not in here in the model. Therefore, that's what we compare the West to. So West has 24 cents higher wages than the East. And again, look at it here. West has 24 cents higher wages than the East. Now, if we look at the South, South has almost a dollar less wages than the East. And that's exactly what we see here. So you see that South has almost a dollar less in wages, average wages, than the East, and so forth. So this is what these coefficients here mean. They directly correspond to the average wages that we see above. Now, if we want to actually switch up the reference categories a little bit, we could have West as the reference category. So you see how all of these are now, all of these here are the other regions here, but we don't have the West. And here in the previous one, we didn't have the East. So looking at this, now we are going to see that this coefficient here is with a minus sign. Why? Because now we're saying that the wages in the East are 24 cents lower than the wages in the West. Now we are if we compare the wages in the South, wages in the South are now $1.22 lower than the wages in the West. And if we go up to the summary statistics here, we can see that wages in the South are basically, these wages are basically $1.22 lower than the wages in the West. Or in other terms, we could actually calculate it from up above here. Well, the wages in the South here were already 98 cents lower than the wages in the East, and uh, and the and then we have the additional 24 cents lower wages that we have for the East versus the West. And that's how this coefficient here is also a composite of this coefficient here plus this coefficient here. And that's how we get that coefficient. So again, we could get one coefficient from the other coefficients very easily. Okay, so now if we include another variable as an independent variable, so let's say everything is the same, but we also include education as a independent variable. Here, that education would also have its own coefficient, and here we would have these ones would no longer be uh, um, these ones would no longer have an interpretation in reference to average wages, but still we could say that wages in the West are 34 cents higher than wages in the East. Wages in the South are 59 cents lower than wages in the East. And here we would be saying that wages in the East are 34 cents lower than wages in the West being its reference category, and wages in the South are 94 cents lower than wages in the West. So that's how we are going to be interpreting these results that we have here. Okay, so continuing on, now let's talk about what happens when we have interaction terms between a indicator variable with non-indicator variable. So here we would have a linear model of wage regressed on education. And let's summarize this model. This is what we see here, where we have basically same intercept and same slope for males and females. Why are we saying this? Well, because female is nowhere to be found in this model. That variable is nowhere to be found in this model. So that's why everything is restricted to be the same for males and females. We're estimating one model across males and females. So here, this is the average, this is the effect of education on wages for both male and females. We only have one. Okay, so if we plot this, this is what we are going to see here. So we want to be plotting the results from this regression. And we would be seeing this is the slope of the regression that we have, and this is how the data looks like in terms of education and wage. So again, one slope for males and females, one intercept, because in this regression model, we do not have any variable here on that represents female. Okay, so now let's run a regression of wage on education and female. And so, uh, so let's run this model and summarize it. Okay, so this is how this model looks like that we have here. So now we have a um, variable education. So we actually have a slope here, which is this coefficient on education, and we have a variable female, and that's the coefficient of female. So what effectively we're doing here is that this model will have the same slope but different intercepts for males and females. So we have the same slope because there's only one education variable. It's not interacted with female or anything. So it's the same slope for males and females or same effect of education on wage for males and females, but we have different intercept because female here is entering as an independent variable. So this is the intercept for male, and for females, the intercept is this one plus this one. That would be a different intercept for females. So in order for us to plot this on a graph, first of all, let's convert the variable female into a factor or a categorical variable for plotting. So the way to do this, we will actually convert it to a factor variable. We're going to pick up the variable female, say that it has two levels, 1 and 0. We would be labeling it as female and male. And then we would be calling this new variable gender, and we would be including it back into the data set. So now if we want to plot using ggplot, here we could plot education on the horizontal line. We would be having two different lines based on gender, and we would be plotting the data set, the actual values for wage and wage hat, which will be the fitted values from this model that we have here that included a female as independent variable. And so here we would be plotting all of that. So let's see what the graph is showing here. And so notice that now we have two graphs, and notice that this is the graph, this is the line for males, and this is the line for females. So notice that the slope is the same for education, which means these two lines are parallel to each other. They're never going to cross each other because we have restrained the slope to be the same. But the intercept here, where it hits the 0, that intercept would be different for males and females. And we already estimated that. And we know that these are those different intercepts that I showed you. So this is how this is going to look like. So the distance here between these two lines would be actually the coefficient on female. So if you're looking at this, the distance between the lines would be exactly 2.27. So the line for females would be 2.27 lower than the line for male. This would be the slope of these lines. So that would be the coefficient on education. The intercept for males would be this one. The intercept for females would be this one minus, plus this coefficient, but because it's a negative sign, will be lower. And that's how you could get all of the statistics that you need to actually plot this line here. Okay, so the final thing that we're going to be doing here is to run a regression of a wage on education and male, just to see how that looks like. And so here's that. Here's this regression results. So if we're going to be running this model of wage on education and male, this is what we're going to see here as far as intercepts and slopes. So notice that the coefficient on education is exactly the same, whether we use male or female as the indicator variable here. What happens if we include the male variable instead of the female variable is that this sign here flips. So the magnitude is the same, the significance is the same, but the sign is reversed. Because now we're saying that males get 2.27 cents higher wages than females. This intercept is different now because this is the intercept for females. If we want to get the intercept for males, we would need to sum up this number plus this number. That's going to give us the intercept for males. So it's basically looking just the opposite of what we had before. Okay, so now we can do a regression of wage on education for females and regression of wage on education for males. The way to actually do this in R, we can actually subset the data where female is equal to 1. Notice that we're using a double equal sign here, and subsetting the data where female is equal to 0. Again, we're using a double equal sign here. And we can estimate the same model of wage on education, but notice now that this one is for females and this one is for males. Notice that in this model we cannot include female or male in it because we already split the data for females and males. Here all the females are 1, here all the females are equal to 0. So we cannot add the variable female or male into these regressions anymore. So that's an alternative way of just estimating these two models separately for males and females. So now what that would afford us is we're going to have different intercepts and different slopes for males and females. So let's see this how this plays out. So you see how we have these are the regression results um, for females that we have here. For female equals 1. So this is for the subset of females, and here we have these are the regression results for the subset of males. So female equals 0. These are the results. So now for these two models, what we're going to have is that both the intercepts and the slopes are going to be different. Why? Because it's different regressions for males and females. So notice that this slope here for females is different than the slope here for males. And this slope here for the intercepts are different, and also the slopes here are different. So here the way to interpret this coefficient is that um, for females, because that's for whom we're estimating this model, for females, each additional year of education brings 45 more cents in wages, and here for males, each additional year of education brings 53 more cents in wages. So let's go ahead and now plot these two and see what we get here. If we're plotting these two, this is the graph that we're going to get. So here we have different lines. This is the line for female, this is the line for male. Notice that now these two lines are not parallel to each other, right? Because they don't have the same slope. So they're going to be crossing somewhere down here. So the slope is different and also the intercepts are different. And this is what we did when we estimate different regressions. And so these dots here, the green dots are also the dots, the data that's available for males. And the red dots here are the data that's available for females. So this line is drawn based on the red dots for female, and this line is drawn based on the green dots. That's the data for males, and that's basically how this graph here looks like. So this is the most, like, we don't have any restrictions on either the intercept or the slope, so they're different for males. They're different for males and females. Okay, so this is how the graph of looking at wage by gender here looks like for males and females. Now, we can estimate this model with one regression. So instead of just subsetting the data and estimating this model here for female and this model here for males, we can accomplish this with one single model, and that is how. Let's go ahead and generate an interaction term between female and education. So here we would have female times education. We would call this new interaction term female times education, like that. And then let's just have a model that we have wages, dependent variable, education. We include female separately, and then we include the interaction between female times education in the model. And let's go ahead and summarize this model. And notice that these are the coefficients here. These are the intercepts. So notice this is an intercept, and notice these are the coefficients on education here. So notice these coefficients here, their magnitude. And so if we're basically looking at this regression here that we have wage, education, female, and the interaction term, notice that this is the intercept that we have here in the regression for males, And this is actually the coefficient that we have exactly here in the education for males. So that's not a coincidence. This has to be like that. And the reason for this is that this is the intercept for males, because if female is equal to 0, that is the intercept for males. And if female is equal to 0, this interaction term here would be equal to 0. So basically the slope or the effect of education on wage for males would be this one. And how we can find the intercept for females is just because female would be equal to 1. We're going to have this coefficient plus this coefficient. That's going to be exactly the coefficient up above in the subset for females. And how we're going to find the slope for females is basically summing up this coefficient plus this coefficient, because for females that's going to be equal to 1. So we need to do this one and this one. And this is going to be exactly that coefficient that we have up here of 0.45. So these two regressions that we can estimate separately are basically incorporated into one overall regression like this, that we have the interaction terms with it. So for us economists, this is the most common way in which we would like to introduce a dummy variable that would generate a different intercept, and then an interaction with another variable that would generate different slopes. Is That's how we do it. We don't typically estimate separate regressions, but like one combined regression like that. Okay, so just to recap one more time, these are the intercepts and slopes for males and females. So basically, if we're just looking at the B, the coefficient on for the intercept for for males is exactly this one. So we're just picking up this coefficient. The intercept for females is the coefficient on females plus the coefficient on males. So if we sum up uh, this coefficient here plus this coefficient here, we are getting this minus 0.99, which was the intercept in the separate regression. If we want to find the marginal effect of education on wage for males, that's basically just this coefficient here that we have of 0.53. And if we want to calculate the same marginal effect, we would need to be summing up this coefficient here plus this coefficient. And when we do that, that's going to be the 0.45. That's going to be exactly, this one would be exactly the number that we see as the coefficient on education in the regression that has the subset by females. Okay, one more important point to mention here is that even though the intercept from male and female is different from each other, actually, if we look at the p-value, it's not significantly different from each other. And the same thing implies here for, even though the co coefficients on the education are different for males and females, they're actually not significantly different from each other. So that's also a very important point to make here, that overall, our conclusion is that actually males and females have the same intercept and have the same slope. So basically the same effect of education on wages. Okay, so now let's go ahead and actually test these differences more formally using an F-test and a Chow test. So in order for us to do an F-test for differences across groups, that is basically a joint coefficient significance, and it's used to test whether the several coefficients are jointly significantly different from 0. So now let's go ahead and again generate some interaction terms. Here we would like to interact female with the variables education, experience, and tenure. And we basically want to know, do women have different effect of education, experience, and tenure on wages than males? And so here is the unrestricted model that we can estimate here. So notice that this is wage regressed on education, experience, tenure. We would be including female as a separate intercept here. And then we would have the interaction terms between female times education, female times experience and female times tenure also in the model. So this is the unrestricted model that has all of these coefficients, and let's call these delta coefficients the coefficients on these all of these terms that have a female in them. Now, if we want to estimate a restricted model where we're saying, well, men and women have exactly the same effect on 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 wages, there are no significant differences across the groups. What what that means is that we would be estimating this model here, where you see that there's no female, so this variable is not included. The interaction terms are not included because these effects are actually restricted to be the same for male and female here. So effectively, if we're testing the null hypothesis that all of these delta coefficients here on the female variable and all of these coefficients on the interaction terms are not significantly different from each other, or we're testing them, are they significantly different from zero or not? That's basically the test that we're doing. Okay, so how we do that is we would be estimating the unrestricted model. This is an F-test, what we learned before. And so here we would be getting the residuals from this model here, from the unrestricted model. We're going to be squaring. This is the sum of squared residuals for the unrestricted model. Q equals 4 because we have 4 restrictions to test. Basically, these are these coefficients here, delta 0, delta 1, delta 2, and delta 3 to test. And now we can calculate F statistic. And basically, to calculate the F statistic, we would be using this formula that we have here, which is the SSR, the sum squares for the residuals. For the restricted model, the sum square for the residuals for the unrestricted model divided by the number of restrictions, sum squared residuals for the unrestricted model, and the degrees of freedom on residual. We have everything here calculated, and we would be basically calculating the F statistic. This is the F statistic here, 16.8. And then we have the F critical value calculated as Q of F for the F distribution, 95%, 0.95, which means at the 5% significance level, these are the number of restrictions. And this is the degrees of freedom for the residual. This is the critical value that we have for the F critical value. So comparing the F statistic to the F critical value, we can already tell that the null is rejected and we have significant results and coefficients are jointly significant. But if we calculate the p-value for the F test, which is p-value for the F-test, giving it the F-stats, the number of restrictions, and the degrees of freedom, and saying that that's not a lower but an upper one-tail test. This is the p-value, which again, you see it's very, very small. So therefore, we're again concluding that we are rejecting the null hypothesis and the coefficients are jointly significant. So what we found here is that there are actually significant differences for males and females uh, in this model. Now, this is done the slow way, but we can do things a lot faster by just using the R commands. And after we estimate the model, what we can do here is linear hypothesis. We're giving it the model 10. So this is basically the unrestricted model. So we're first estimating the unrestricted model. And then all we need to do after this is basically just say the coefficient of female equals 0, the coefficient on the interaction equals 0, like that. So notice that these are again not that the variables are equal to 0, but the coefficients on these variables are being tested if they're significantly different from 0. And this is what we see here. So this is the F statistic here, and that is the p-value. So if you look up above, that's exactly the F statistic that we calculated manually in a slow way, and this is the p-value. So again, if you want to test for significant differences, all we have to do is just estimate the unrestricted model and then basically do a linear hypothesis test testing that all of these coefficients are jointly significantly different from 0. Okay, so the last thing that we will do here is we will do a Chow test for significant differences across groups. So what we did before with an F test, we can do it using the Chow test. So Chow test is effectively an F test for significantly different coefficients between two groups. So instead of estimating one unrestricted model, two separate models are estimated for each group. So here's what we're going to do. This is the restricted model that we have. And so basically we're going to have education wage equals to all of these variables. And so this is going to be one of the models that we have, a restricted model. Now, we can estimate a model for females and a model for males separately. Okay, so this is the model for females. Notice that we're just updating this one model that we have, the restricted model before, because it doesn't have any interaction terms. So here's the model that we have for females. All we have to do is just subset it for female equals 1. And the model for males would be, we're going to subset this model for males. Now notice that the model 11 from up above does not have any interaction terms here. Uh, so no interaction terms here. So this was the same as the model 9 here. So it basically has no interaction terms here. And so, we are estimating this model separately for males and females. And the way to calculate the Chow F statistic is basically look at the um, sum squared residuals for the restricted model that we have up above from here, where we have both of the um, uh, groups estimated together. And then we have, this is the sum of square residuals for females and the sum of square residuals for males. And we're basically using this formula, which is equivalent to the F statistic above. And we're calculating the F critical value and the P value for this F test. And here is the F critical value that we're estimating. And here's the test statistic, and this is the critical value. So notice that actually these two are exactly the same numbers as we had them before. And that is the p-value for the F test. Because again, we're testing exactly the same thing. We're using a different approach for the Chow test. So the difference again is that the F test that we did above estimates a restricted model where all of the coefficients on the interaction terms that have female are put equal to 0, and an unrestricted model. Whereas here we only have restricted models here where we are basically subsetting, we have the restricted model here, but then we're subsetting that restricted model for female and for males, and we're estimating two separate models, and then we're using the sum squared residuals from them to calculate the F statistic. So that's how we're testing jointly whether these coefficients are significantly different from 0. So this concludes this presentation. Thanks for watching.